This is section 10.1, part C, significance test for p1 minus p2. An observed difference between two sample proportions can reflect an actual difference in the parameters, or it may just be due to chance variation in the random sampling or random assignment. Significance tests help us decide which explanation makes more sense. The null hypothesis has the general form of h sub 0 is p1 minus p2 equals the hypothesized value. We will restrict ourselves to situations in which the hypothesized difference is 0. Then the null hypothesis says that there is no difference between the two parameters, or h sub 0 is p1 minus p2 equals 0. Or the alternative, an alternate way to write this is p1 equals p2. The alternative hypothesis says what kind of difference we expect. So researchers designed a survey to compare the proportion of children who come to school without eating breakfast in two low-income elementary schools. A simple random sample of 80 students from School 1 found that 19 had not eaten breakfast. At School 2, a simple random sample of 150 students included 26 who had not had breakfast. At School 2, a simple random sample of 150 students included 26, again, who did not eat breakfast. More than 1,500 students attend each school. Do these data give convincing evidence of a difference in the population proportion? So we need to state appropriate hypotheses for the significance test to answer this question. Define any parameters you use. So our hypotheses can be, our null hypothesis is that there's no difference, so p1 minus p2 equals 0. The alternative hypothesis, we don't know which school would have a higher proportion who don't eat breakfast. We just assume they're not the same, so we can let our alternative hypothesis be that p1 minus p2 does not equal 0. Where p1 is the true proportion of students in School 1 who did not eat breakfast, and p2 is the true proportion of students in School 2 who did not eat breakfast. If the random, normal, and independent conditions are met, we can proceed with calculations. To do a standardized p1 minus p2 to get a z-statistic, for your test statistic, you're going to do statistic minus parameter over the standard deviation of the statistic. Or in this case, it'll be p hat 1 minus p hat 2 minus 0, because we're going to do all of our hypotheses, that p1 minus p2 equals 0, over the standard deviation of the statistic. If p sub 0 of h sub 0, which is p1 minus p2 equals 0, is true, the two parameters are the same. We call their common value p. But now we need a way to estimate p. So it makes sense to combine the data from the two samples. This pooled or combined sample proportion is called p hat sub c, which is the count of successes in both samples combined over the count of individuals in both samples combined. Or p hat sub c is equal to x1 plus x2 all over n1 plus n2. Recall that the standard deviation of p hat 1 minus p hat 2 is given in the equation below. If we use p hat c in place of both p1 and p2, in this expression for the denominator of the test statistic, we would end up with our z-score equaling p hat 1 minus p hat 2 minus 0 over the square root of p hat c times 1 minus p hat c all over n1 plus p hat c times 1 minus p hat c all over n2. Since the normal condition is met, this will yield a z-statistic that has approximately the standard normal distribution when h sub 0 is true. Here are the details for the two sample z-test for the difference between two proportions. So, suppose that the random, normal, and independent conditions are met. To test the hypotheses of h sub 0 is p1 minus p2 equals 0, first find the pooled proportion, p hat c, of successes in both samples combined. Then compute the z-statistic. We find the p-value by calculating the probability of getting a z-statistic this large or larger in the direction specified by the alternative hypothesis. It would be correct to check the normal condition using the pooled combined sample proportion p hat c. Just confirm that n1 times p hat c and n1 times 1 minus p hat c, n2 times p hat c, and n2 times 1 minus p hat c are all at least 10. So you're going to check the number of successes and number of failures using our combined proportion p hat with the sample sizes from p1 and p2 to check that 10%, that at least 10. They are both or all at least 10. Researchers designed a survey to compare the proportion of children who come to school without eating breakfast in two low-income elementary schools. A simple random sample of 80 students from School 1 found that 19 had not eaten breakfast. At School 2, a simple random sample of 150 students included 26 who had not eaten breakfast. More than 1,500 students attend each school. Do these data give convincing evidence of the difference in the population proportions? Carry out a significance test at the alpha equals 0.05 level to support your answer. So we're going to need to start with the state. Remember, in the state, we need to give our null and alternative hypotheses. We need to define our parameters, and we need to give the significance level. So our hypotheses are that h sub 0 is p1 minus p2 equals 0. The alternative is p1 minus p2 does not equal 0, where p1 is equal to the true proportion of students at School 1 who did not eat breakfast, and p2 equals the true proportion of students at School 2 who did not eat breakfast. And we're going to do this at a alpha equals 0.05 significance level. Next, for our plan, we're going to state what method we're going to use, and then we're going to check our conditions. So if the conditions are met, we should perform a two-sample z-test for p1 minus p2. To check the random, the data were produced using two simple random samples, 80 students in School 1 and 150 students in School 2. Now, to check the normal conditions, we can find the number of successes at School 1 and the number of failures in School 1, the number of successes in School 2, and the number of failures in School 2. And since all of these are at least 10, we know the normal condition has been met. Next, we need to check for independence. So 10 times 80 would give us 800 students at School 1, and 10 times 150 gives us 1,500 students in School 2. And we were told in the problem that there are more than 1,500 students at each school, so the 10% condition has been met. Next is our do. So we know that our sample size for population 1 is 80, and the probability of success, or our p hat for that one, is 0.2375. The sample size for population 2 is 150, and p hat 2 is equal to 0.1733. The pooled proportion of students who did not eat breakfast in the two samples, we can find our p hat c, which is equal the number of successes in group 1 and group 2 added together, and the sample sizes of group 1 and 2 added together. So 45 out of all 230 students who were sampled did not eat breakfast. So our p hat sub c is 0.1957. Now let's find that test statistic. Our z value is going to be p hat 1 minus p hat 2 minus the hypothesis, which was 0, all over the standard deviation for the pooled data. So we're going to do 0.2375 minus 0.1733 minus 0, all over the square root of the probability of success for the combined times the probability of failure all over the sample size for 1, plus probability of success times probability of failure all over the sample size for population 2. And that's going to give us a z-value of 1.74. To find our p-value, we need to find the area under the standard normal curve. Now remember, 1.17 is going to be towards the right, and if you look at your table, it's going to find you the area to the left of that. So we need to do 1 minus the area. So if the area is 0.8790, if we do 1 minus that, that'll tell us the area to the right, or the area greater than. But this was a not equal to problem, so this is a two-tailed test. So once you find that area, you will have to multiply it by 2 to find the p-value. And this is going to give us a p-value of 0.2420. Last thing we need to do is conclude. So since our p-value of 0.2420 is greater than our chosen significance level of alpha equals 0.05, we fail to reject the null hypothesis. There is no sufficient evidence to conclude that the proportion of students at the two schools who do not eat breakfast are different. Exactly what does the p-value in the previous example tell us? If we repeated this random sampling process many times, we'd get a difference in sampling proportions as large or larger than one actually observed about 24% of the time when the null hypothesis of p1 minus p2 equals 0 is true. With such a high probability of getting a result like this just by chance when the null hypothesis is true, we don't have enough evidence to reject the null hypothesis. We can get additional information about the difference between the population proportions at school 1 and school 2 with a confidence interval.